a little review of water because it's really special and it's what most things are dissolved in on the planet that helps a lot of chemistry happen. So it's we've talked a lot about it, but let's just put it all in one place. Water is the only substance on Earth that exists in large quantities in all three states, solid, liquid, and gas. So let's watch a little video about it, take some notes.
Water is surprising stuff. The most common of compounds, water can be found in nature as a solid, a liquid, or a gas. Sometimes all three states exist at the same time. One of the surprises of water is that it expands when it freezes, making it less dense than liquid water. Consequently, glass containers of freezing water will burst, and ice will float rather than sink. Although water has an unusually high boiling point for such a light molecule, 100 degrees Celsius, water can be seen boiling up to the surface in some hot spots on Earth. The fact that water remains in the liquid state between 0 and 100 degrees Celsius makes life possible in a wide range of environments. Water is probably best known for its dissolving properties. The attraction of water molecules for itself and other molecules makes water very efficient at dissolving many ionic and covalent substances.
Nice. Now let's see why those things are so important. All right, so they talked about water being able to dissolve, and that is all about the geometry. If you remember, water has this unique shape, which is kind of like Mickey Mouse's ears. So he's going to be around a few times during this video. It's that shape because it has two bonded and two unbonded pairs, which is the bent molecular shape. 104.5 degrees at the angle, and that makes this end negative and this end positive. That gives it a lot of interesting properties because with slightly polar compounds, you're going to have them sticking together. So that's called hydrogen bonding when it's hydrogen that's attached to something really electronegative like oxygen or fluorine or nitrogen or chlorine. So these dashed bonds here, these are hydrogen bonds, all the ones between molecules. They're not as strong as covalent or ionic bonds, but they do allow water to stick together pretty tightly. There's also the covalent bonds, which are in the compounds between the oxygen and hydrogen, where they're actually sharing electrons. So which one breaks during melting or boiling? That would be the hydrogen bonds. Good. Which one is stronger, do you suppose? That would be the covalent bonds, because boiling does break the hydrogen bonds, but it can't break the covalent bonds. You need electricity to do that. So which one breaks to give you hydrogen and oxygen? Okay, as I just said, that would be the covalent bonds, because that's when you break water into its elements, and therefore you would have the separate elements and no longer water molecules. But that would require electricity, lightning, something like that. Otherwise, it won't break down. It's good because that's safer that way. So because of that, you have some special properties. For instance, ice, the solid version of water, floats in the liquid. And that is pretty cool. It's the only liquid that does that. And if you notice with this molecular picture, the way the molecules line up when they bond and hydrogen bond in a solid, they leave space in between because of their shape. And so that's why they expand and they float. They also have very high surface tension. You've seen water drop, especially if you get on a nice waxy car. And that is because of that hydrogen bonding going on between all the molecules. The ones at the surface don't have any water molecules to attach to above it, and so they're being pulled very tightly around the surface and inside, and so they form that really nice tight droplet. They also have what we call capillarity because they stick to each other and they stick to the sides of thin tubes. You may have seen this trick in elementary school, and I'll try to have some available, where you put colored water in with some celery or some carnations, and the flower goes up into the plant. And that just shows that water has capillary action, and it can be pulled up into thin tubes. Redwood trees that are 200, 300 feet high have water going up the xylem, I believe, if I'm remembering correctly. Now that is helped by the transpiration that happens at the leaves. That helps lower the pressure and helps the water pressure help push it up. But it's also because of water's great hydrogen bonding ability. It also has a very high heat capacity. In this picture, you've got 1 or 2 paper cups. One paper cup was just a plain paper cup, burns very easily. In this one, there's some water in there. Remind me to demonstrate this to you in class. With the water, the cup doesn't catch on fire. Why is that? First, you might ask, as Mickey does, what specific heat capacity anyway? Well, specific heat capacity is the number of joules it takes to raise the temperature of 1 gram of substance by 1 degree Celsius. You use this in integrated science when you did your burning peanut lab or burning Cheetos or something like that. You had a heat capacity of something that absorbed or released heat. It's just this ratio of joules per gram degree Celsius. So we could calculate how much energy it would take to heat 10 grams of water from 20 degrees Celsius to 100 degrees Celsious. I'm going to have to remind you of the relationship. So that is, I'm going to put it up here. You can put joules, which is a measure of energy. That would equal the heat capacity, which is symbolized with the C at a constant pressure. So the heat capacity of a substance times its mass times its change in temperature. So if we do this for water, it would take, we've got a mass of 10 grams, temperature change of 80 degrees, and the heat capacity as water is one of 2 different numbers. It's either 1 calorie per gram degree Celsius, or it is 4.184 joules per gram degree Celsius. I put joules up there, but down here I'm going to do it in calories first. So 10 times 80 is 800 calories needed to heat water up that 80 degrees Celsius. If I was going to do it in joules, I could use 4.18 joules per gram degree Celsius, just a different unit. We'll come back and use those in class a bit more later. Water dissolves many ionic substances. It's called an electrolyte when water gets ions dissolved in it. So water lands on, when it rains, the water can hit the earth and run back down into the ocean, and that's why the ocean is salty, because there's lots of salt in the soil and the rocks, and the water dissolves it and sends it out to the ocean. That's why the ocean is salty, because even when the water re-evaporates, the salt is left behind. And all tap water and almost all water has some salt dissolved in it unless you buy distilled. So that's why you want to be really careful not to have your hair dry or dry your hair while you're in the bathtub. It will conduct that electricity and you'll be a fried puppy. All right, now one great demo, which I will also try to do in class, but I want to show you right now, is called the electric pickle. To make a pickle, if you don't know, you take a cucumber and you soak it in salt and vinegar. And then, here's a cool thing that you can do with it live in class, because I don't have the right demo queued up. All right, the process by which those charged particles in an ionic solid separate in water is called dissociation. You can see in this diagram where you've got a salt crystal here, you got little water molecules, and the water molecules are attracted to the ions with the different charged sides of the water. So if you've got a negative ion, you'd have the positive hydrogen side attached to the ion, and it's able to pull those ions out away from the crystal. If you've got a sodium positive ion, you've got the negative oxygen side of the water that pulls it away. Let's watch a little video.
Sodium chloride crystals are held together by attractive forces between the positively charged sodium and negatively charged chloride ions. When a crystal of sodium chloride is placed into water, the hydrogen ends of polar water molecules attract the negatively charged chloride ions and gradually surround them. Likewise, the oxygen ends of water molecules are attracted to and surround the positively charged sodium ions. The hydrated ions drift away into the solution, allowing new water molecules to surround newly exposed ions. Gradually, the entire crystal dissociates into solution.
Cool. All right, so here's how we write an equation for this. And we've done this before. We've written ionic equations. So just to show the solid dissolved in water. The water's not actually reacting, so that's why it's kept just as a condition to make sodium ions and chloride ions. Water can dissolve other things too, not just ionic compounds. It can dissolve solid or covalent compounds. So in here, not including the water molecules, this is a sucrose molecule. Around it. And if you notice, sucrose has OHs all around the periphery of the molecule. Those are polar, just like water is polar, and allows it to hydrogen bond. And so therefore water can stick to them, and even though it's a big molecule, it's able to dissolve it away. All right, so in order to dissolve in water, what characteristics do you need to have? If you thought it's charged or it's polar, that is correct. What things can't dissolve in water and why? Well, that would be non-polar things that don't have the ability to stick to water. So things like lard, tar, oil, wax, they don't dissolve in water, but they stick together. All right, so let's talk a little bit about concentrations because we started already with molarity in class. So there's some terms that chemists use differently than regular folks, the way you might use them at your home. Concentrated and dilute are important terms in that way. There's concentrated, which means lots of ions in solution, and dilute, which means few ions in solution, but it depends on the strength of what's dissolved. So if you were talking about this tea, you would say concentrated and dilute. You would not say strong and weak because it's the same substance and strong and weak are fundamentally different in chemistry. So we try to have our language a little bit more precise. We say concentrated, which means lots of moles per liter or lots of ions per volume, and dilute, which is few moles per liter. So strong and weak in chemistry mean, strong, for instance, means that there's lots of ions in a solution. For instance, hydrochloric acid or sulfuric acid are called strong acids because they 100% dissociate, means they break into ions. The HCl in water produces hydrogen ions and chlorine ions, and none of the HCl stays as a molecule, not even a little bit, not even one. Weak acids are the ones that are more likely to be in your food because they're a lot safer, because they provide few ions in a solution. Vinegar, carbonic acid, because of all the molecules in the water, only a very few of them, like a millionth of all the molecules, break into their ions. So strong and weak means the potential for having lots of ions. Strong always has lots of ions in solution. Weak has always few. Concentrated and dilute are what's actually in the solution. Okay, something else that will be useful to us talking about solutions is solubility curves. Here's a solubility curve of many different substances all in one graph. They tend to be written as grams of solute dissolved per 100 grams of water. It's important, over a certain temperature range. And as you can see, most of these lines have a positive slope. The solubility increases as the temperature rises. And that makes sense. Water is going faster, it's able to pull them apart. The one here that's prominently going in the opposite direction is ammonia. And that's important because it's a gas. And gases, when they get heated up, rather than sticking to the water more, they're going to escape into the gaseous state. Okay, so try to review that for yourself. It shows how many grams of something can dissolve at various temperatures in 100 grams of water, so it's a constant volume. Most lines slope up because solids get more soluble in water as temperature rises. Gases tend to reduce their solubility. Cerium sulfate is a solid, and I don't know why it has a downward slope. So just know gases tend to go down, solids tend to go up. All right, so let's see if we can read this. How much potassium chloride, here's potassium chloride, could dissolve in 100 grams of water at 50 degrees Celsius? So if we find the 50, 50 degrees, you've got right there. It's just a little above 40 grams, like 41 grams. Dissolves in 50 degrees Celsius water in 100 grams of water. All right, a couple more terms. Unsaturated versus saturated. If the amount of solid dissolved is less than the maximum that could be dissolved, the solution is called unsaturated. If a solution which holds the maximum amount of solute per amount of the solution under the given conditions, it's saturated. And a supersaturated contains even more solute than the useful maximum amount. Here's a little story to help you understand that. So my dad, Wilford, he likes to have a bowl of grape nuts flakes every morning. He's 91, been doing it as long as I know him. And when he pours his milk on the cereal, probably some of the sugar from the cereal dissolves, and it would become an unsaturated solution, a little bit of sugar in the milk. Now he likes to add lots of sugar. He adds 8 teaspoons, exactly 8, no more, no less, every day to his bowl of cereal. Now, because he adds so much, it can't all dissolve, and the milk is holding the maximum amount, and the solution is saturated. That leaves some solid sugar on the bottom, so he always stirs it up a little bit so that he can get some of the solid mixed in with his milk and enjoy his very sweet cereal. Now, he wouldn't be able to supersaturate it because to supersaturate something requires that you heat it up so that more can dissolve. All right. So let's use the graph from the last page to determine if the following are unsaturated, saturated, or supersaturated. A solution that contains 70 grams of sodium nitrate per 100 milliliters of water at 30 degrees Celsius, and a solution that contains 60 grams of dissolved KCl per 100 mils of water at 80 degrees. So look on the graph and see if you can determine whether they're saturated or unsaturated or supersaturated. A is unsaturated. Sodium nitrate can have more dissolved per 100 grams of water at 30 degrees Celsius, more than the 70. But if 60 grams of potassium chloride are dissolved, then that means it must have been supersaturated, because at 80 degrees it should not be able to hold that much solute. Okay, last topic before we end for today. Concentration units. They are a ratio comparing the amount of solute to the amount of solution or the solvent. For example, there's percent by mass, percent by volume, part per million, part per billion, and molarity. Molarity is the most useful. It's moles of solute per liter of solution. We've already had some good practice with that. But let's go ahead and try calculating one. If you were going to make 1 liter of sodium chloride and you wanted it to be 0.15 moles per liter, then how many grams would you need? Pause, calculate, and then come back. Okay, it should be 8.8 grams of sodium chloride needed. And then the process, as you did in lab, is you weigh out the necessary amount of solid, put it in the volumetric, dissolve it in water up to the line, and put it in a labeled stock bottle. Okay, one last example and then we'll stop. How would you prepare 5 liters of a 1.5 molar solution of glucose? How many grams would you need is really the key. So again, pause, try to do the calculations, and check the answer when you're done. All right, you would need 1,400 grams of glucose, and you'd add that to a 5-liter flask and add water to that whole 5 liters. Hopefully you got that right, and hopefully